Welcome back to Mathematics. Today we are doing a HSC revision lesson in the Extension 1 course looking at applications of vectors. This is a pretty challenging topic. Definitely a lot of high-level E3, E4 questions coming out of this topic in recent HSC. So we're going to do a broad spectrum, starting with some easier ones and then finishing off with some more painful ones to give you a bit of an idea of the variety you can see in this topic. Also, side note, after 4 long years, I finally got myself a new laptop. So hopefully the picture and audio quality could be a bit better. The explanations and the editing will still be dog shit as always because this is Mathematics, but hopefully at least it looks a tiny bit better. Okay, let's dive in. So the topics we're covering today are focusing on projectile motion, geometric proofs, and velocity acceleration proofs using vectors. So let's kick off. This one is from the 2020 sample exam. It wasn't in the actual 2020 exam, but it was a kind of fake exam posted by NESA that was the same sort of quality as an HSC exam. Here is a relatively easy introduction to projectile motion type question. We have a particle fired from the origin, initial velocity 18 meters per second, 60-degree angles horizontal. Equations of motion are the horizontal acceleration is nothing and the vertical acceleration is gravity, which is approximated to -10. Starting off with show that the x displacement is equal to 9t. All right, so that's where we're going to begin. Now with any projectile motion question, if you haven't been provided the initial conditions for velocity, that's where you should start. So we're going to look at what's happening to the velocity initially. Initially, we are going on an angle of 60 degrees with a velocity of 18 meters per second. So now we need to figure out some expressions for the initial horizontal and the initial vertical velocity in this right angle triangle that I've inconveniently left the right angle out of. I apologize. So when you do a bit of trigonometry, what you will see is that this side here is going to be equal to the hypotenuse length times cosine of the angle 60. Okay? Do a bit of trigonometry here and rearrange it. You're always going to get that the horizontal is hypotenuse cos angle. And because cos 60 is equal to a half, that's equal to 9 because it's 18 times a half. What you're going to see for your vertical component is the same thing but with sine. It's going to be hypotenuse sine of the angle across from it. So we have 18 sine 60. Sine 60 is root 3 divided by 2. So when we times that by 18, we're going to get 9 root 3. So initially in the x direction, velocity is 9. Initially in the vertical direction, velocity is 9 root 3. That's going to be very useful later on. Okay, so we're going to start with our x acceleration being equal to 0, and we're going to try get to x equals 9t by integrating twice. So first of all, to get our x velocity, we need to integrate our acceleration. So acceleration is 0, and when you integrate nothing with respect to t, nothing integrates to a constant, or 0 plus c. And now because we've shown that the velocity is constant, it's going to have to be the same thing as your starting value, which we saw over here. Initial x velocity is 9, and so it's going to stay as 9 the entire time. Okay, so x velocity is equal to the constant value that we got from this triangle, so it's equal to 9. Okay, now we have our x velocity. We are going to integrate that again to get our x displacement. So integrating velocity with respect to time is getting us displacement. Integral of 9 is 9t plus a constant. And now once again, subbing in our initial conditions, when t is equal to 0, we are at the origin. So our x displacement is 0. So we get 0 equals 9 lots of 0 plus c. So we've figured out that c is nothing, which means that x is equal to 9t as required. I kind of forgot that last little bit there. So yeah, a bit of a stitch up question for 1 mark because you've got to get your initial conditions and you've got to integrate twice to get 1 mark, but nothing here is screaming high level of difficulty yet. Moving on to the y equation, we're now going to show that the y displacement is equal to 9 root 3t minus 5t squared. Starting off with the same place, we are going to start with our acceleration and we will integrate that to obtain our y velocity. So y velocity, y dot, equal to the integral of acceleration with respect to t. So minus 10 is going to integrate to minus 10t plus a constant. Now, initial conditions, when t is equal to 0, the y velocity, as we got from our triangle before, was equal to 18 sine 60. So t equals 0, y velocity 18 sine 60, which is 9 root 3, which gets us our value for c. That gets us our y velocity being equal to minus 10t plus 9 root 3. Okay, so in all these cases, all your constants are going to be your initial conditions. So in this case, c was equal to initial y velocity. Now last step, to get our y displacement, we are going to integrate our y velocity. So y is equal to the integral of the velocity equation, once again with respect to time. So minus 10t is going to turn into minus 10t squared on 2, and the 9 root 3 will become 9 root 3t. And of course, when we raise the power here and divide by 2, 10 turns into 5. Once again, get a constant, which we will ascertain, that's a fun word, by using our initial conditions. When t is equal to 0, we are at the origin, which means y is equal to 0. So we have 0 equals lots of zeros plus c, and so we get c is our initial displacement vertically, which is just nothing. Which gets us our equation required for 2 marks, y equals minus 5t squared plus 9 root 3t. Okay, so far all very straightforward stuff. Quite often in the HSC they don't get you to prove these results, they just give them to you and then get you to do cool stuff with them, which we'll see in a later example in this video. For part 3, we're going to find the Cartesian equation. So we have 2 parametric equations in part 1 and 2 because we have x and y in terms of the extra parameter, which is t. We are going to try and combine these two into one equation relating x and y with no t's present. So we have our x equation and we have our y equation, and we're trying to combine these two together. So the way we're going to do that is we're going to take the simpler one, which is quite clearly the x equation, and we're going to rearrange this to make t the subject. So dividing the 9 across, we get t equal to x divided by 9. Now we can substitute this value of t into our y displacement equation, written up like here. I don't know why there's a c there, that should be gone, I apologize. But when you sub it in, we get 9 root 3 times x on 9, because that's t, and we get minus 5 times x over 9 squared. Now we're just going to simplify this a bit. The 9's cancel here, so we get root 3x, and then on the end, we're going to get minus 5x squared over 9 squared, which is 81. So root 3x at the front, minus 5x squared over 81. There we have an equation relating y and x, so this is the graph of our parabolic shape that our projectile motion is portraying. Okay, coolio. On to the next one, which is from an actual HSC. It's an E3 level from the 2022 HSC exam. It's a geometric proof involving vectors. We have 3 points chosen on a circle with a center at O. We have vector A, vector B, vector C here being 3 radii of the circle. And we have vector H here, which is A plus B plus C. So it's the resultant vectors of A, B, and C all plussing together. For 3 marks, we're trying to show that BH and CA are perpendicular. All right, let's make some space and dive in. So first thing we're going to need is we're going to set up what we're trying to prove. If you're being asked to show that 2 vectors are perpendicular, it means you're trying to show that they have a dot product of 0. Okay, I explained in my vectors video why perpendicular corresponds to a dot product of 0, but here is our target for now. Okay, we also need to know that BH, the vector BH, can be written as H minus B, once again from my vectors video. So from B to H is H minus B, and the vector from C to A is A minus C. Okay, so it's the second letter minus the first one is the quick little shortcut to get your 2 vectors. Now we're going to use some useful information from the question that H is actually equal to A plus B plus C, and we can sub that into our first bracket here. We can change H to be A plus B plus C, because now when you take that value of H and you subtract B from it, well, these 2 B's, the plus B vector and the minus B vector, are going to cancel out, and it's going to leave you with A plus C. So putting that into our equation here, H minus B is actually equal to A plus C. And now we have a much more friendly looking equation. Now we can sort of expand out this dot product using the same logic as a difference of squares. It's kind of like you've got A plus C times A minus C. You can just do the first 2 dot producted together minus the second 2 dot producted together, because when you do the big expansion, the bits in the middle are going to cancel each other out. So expanding that out using difference of squares logic, we have A dot A minus C dot C. Okay, when we get to this point, we can use a really useful vector fact that comes up in a lot of vector proof equations. It's been in almost every HSC for the last few years. The fact is that when you do a vector with a dot product of itself, it's the same thing as the magnitude squared. All right, this result in red is definitely worth memorizing. In a later question in today's video, we're going to prove this, but for now, just trust me, this is true and it's very useful. That means we can write our blue expression here. A dot A is going to be equal to magnitude A squared, and C dot C is equal to magnitude C squared. So it looks like this. Now remember, the whole goal here is to show that this whole expression here on the right is equal to 0. And if you think about A and C and the lengths of A and C, we said at the very start of this question that A and C are both radii of this circle. If they're both radii, it means they have the same length, which means they have the same magnitude. So this magnitude squared minus this magnitude squared is going to be 0, because these two lengths are the same, which means their squares are the same. And so we can say equal radius lengths gives us 0, because magnitude A is equal to magnitude C. Therefore, we've proven that the dot product is equal to 0, so we've proven that these two vectors must be perpendicular. QED. Okay, that was fun. The one we're going to do later on is much less fun, so stay tuned for that horror. Okay, moving on to an E3 level question on projectiles from 2021. This is much more challenging than the one we did earlier today. It's a 4-mark question, so there's a fair bit of work to do here, but none of it is super strenuous as long as you understand the logic and sort of how to set up your equations. We have an object fired from h meters above the origin, so we've got an initial height, initial speed v, angle theta to the horizontal. Here are the equations. This is our displacement vector, which means right here is our x displacement, and right here is our y displacement, and we are not required to prove this. Person standing in an empty room. The room is 3 meters high, throws the ball to the far side of the room. Ball leaves their hand 1 meter above the floor, so that's our initial height. H is equal to 1. And above the floor and 10 meters from the far wall. So the wall we're throwing at is 10 meters away. Initial velocity is 12, so capital V is 12. Angle is 30 degrees, that's our theta. To the horizontal. Show that the ball will not hit the ceiling of the room, but that it will hit the far wall without hitting the floor. Okay, so a part that makes this question a bit more challenging is that this is the entire question, just this wall of text with a generic equation and 4 marks. They haven't given you any sort of picture to visualize what's going on here. So this question gets much more simple if you go to your writing booklet and you draw what's going on. It looks like this. We are throwing a ball from 1 meter high. We're throwing it at 30 degrees, 12 meters per second. We are trying to show it doesn't hit the 3 meter high wall, and we're trying to show that it's going to hit the wall where it is 10 meters away. Okay, so the way we're going to achieve this is we're going to try and find the maximum height of this projectile, and we're going to show that it's less than 3. We're also going to show that if this wall wasn't here, the ball would land later than 10 meters away. If it's landing later than 10 meters away, logically it's got to hit this wall before it lands. That's the idea here. So we're going to build our equations and then prove those two statements. So starting off with our info from the question, x displacement is equal to vt cos theta. We now know that v is equal to 12, and we know theta is equal to 30. So we have 12 cos 30t. Cos 30 is equal to root 3 on 2. So when we simplify this by multiplying it by 12, we're going to get 6 root 3t for our x displacement. Getting our y equation, here's the one given to us by the question. Subbing in v equal to 12 and theta equal to 30, we get minus 5t squared, 12 sine 30t plus 1. Sine 30 is equal to a half, and 12 times a half is 6. So we have our y displacement right here. So we're getting towards an answer now. So our two goals are to show that the maximum height is less than 3, and we're trying to show that the range, or the place where the ball lands, is later than x equals 10, so it hits the wall before it lands. Okie dokie, so to do this, we are gonna need our x and y displacement. We're also gonna need our x and y velocity. So when you have your displacement equations and you want to find your velocity equations, all you got to do is differentiate them. So the derivative of this is 6 root 3, and that's our constant x velocity. Differentiating our y equation, we get minus 10t plus 6, and this is our vertical velocity equation. So if we're trying to find the max height of a projectile, the max height is where it stops traveling up and starts traveling down. So that's where your velocity goes from, in terms of verticality, goes from positive to negative. So we're trying to see where the y velocity is equal to 0. So we're just going to make some space, and we're going to keep the useful equations here, x and y displacement, x and y velocity. Like I said, setting the y velocity equal to 0 is going to get you the time that the ball turns around, so it finds the maximum height for you. We're going to minus the 6 across here. We're going to divide both sides by negative 10, and we end up with t equals 0.6. That's the time when the ball reaches the peak of the curve, the maximum height. So we need to see if that height is less than 3. So we're going to take t equals 0.6 and we're going to substitute it into our height equation, which is the y displacement. So taking y and letting t equal to 0.6, substituting this in and calculating this value, we get an answer of 2.8. And would you believe that 2.8 is less than 3? So we've proven that the maximum height achieved by this projectile is less than the maximum height of the room. So we've shown that the ball does not hit the ceiling. So we're already halfway there. Now to finish off this question, we've got to prove the statement in red, which is that the ball is landing after x equals 10. So if you want to find where the projectile lands, you want to find the range. You want to find when the y value is equal to 0. Okay, you're trying to find when the height goes from the ground back down to the ground. So landing time is when y is equal to 0. So let's figure it out. Setting our vertical displacement equal to 0 up here. Okay, trying to see when it lands. We have a pretty scary looking quadratic here. We can times everything by -1 if you want to, or you can just dive straight into the quadratic formula. We have negative b out the front, plus minus 6 squared minus 4 times a times c. Then underneath we have 2 times a. Okay, so substituting our 3 values into the quadratic formula, simplifying a little bit, we get minus 6 plus or minus root 56 over minus 10. We can simplify even further by writing root 56 as the square root of 4 times the square root of 16. So we can simplify root 56 to 2 root 14. We can divide everything by negative just to make this 6 and this 10 positive, which is nice. And now we're going to get 2 values. We're going to get a plus and a minus. The minus is going to go negative, which is not really useful for this question because in this dimension, time can't be negative. So we're really only looking at the positive answer, which is 6 plus 2 root 14 over 10. And we can simplify that even further, because everything here is an even number. So we can cut 6 in half to 3, get rid of the 2, and cut 10 in half to 5. So this calculation is going to get us the time when our ball lands. And so we're trying to find the x value when it does land. So we should take this time and we should sub it into our horizontal displacement, which is up here, x equals 6 root 3t. And let's see what we get. So x equals 6 root 3 times t, where t is 3 plus root 14 over 5. Calculating this, we get a value of approximately 14 meters. So we're showing that if the wall wasn't there, it would land after 14 meters. And because the wall is before 14 meters, we have shown that we are going to hit the wall before we land. So there we go. There's the entire 4-mark question. Built it up, made your equations, and then know how to use them. Okay, so when you do a lot of projectile motion questions, you'll see the same question types and you will learn how to use these equations more confidently. But yeah, it's a lot of content, so you need to get practicing if you want to be ready for the HSC. Okay, and finishing off with a couple of E4 level questions. Here's one from 2021 as well. It's 3 marks and it's just a bit of text with no picture to help you. We have a plane traveling to a destination on a bearing of 63 degrees. So that's where the destination is. Engine flies at a constant 175 kilometers per hour. However, there's a wind from the south that is at 42 k's per hour. On what constant bearing to the nearest degree should the direction of this plane be set in order to reach the destination? Okay, sweet. So this isn't actually that challenging of a question, but it was an E4 level question in 2021 because a lot of people really struggle with it. The reason this is so challenging is because you've got to draw your own picture. The HSC did not provide you a picture. However, if you know how to read this wall of text and turn it into a good picture, it's going to make this a really straightforward 3 marks. So let's visualize this. We need to travel, or the destination we want to travel on is on this green line, which is a bearing of 63 degrees. However, we can't fly on this green line because the wind coming from the south is going to push us up. So we need to fly a little bit below that line so that when we have the velocity of the plane and then the velocity of the wind together, we make this little triangle and we end up at the end of the green line. So we need to figure out what this angle is here, so we can figure out what bearing we need to fly on to then account for the wind to end up at the target, which is on a bearing of 63 degrees. So this picture right here is going to make things much more simple to figure out. We're going to put a 63 in here because this north line and this southerly wind are both parallel, so we have alternate angles. And the goal is to figure out this angle here. We'll call it theta because we can add this to 63 to get our total bearing for the 175 plane to then account for the 42 wind and then end up on target. So if you look at this and you're trying to find theta, this is something you probably could have done a couple of years ago when you learned about the sine rule, because we have an angle across from a side and an angle across from the side. So we've boiled this down by creating a really useful picture into a sine rule question. So let's dive right in. We have sine theta over 42 is equal to sine 63 over 175. And now we're just going to solve for theta. So we're going to move the 42 across, and then we're going to take sine inverse. So like this, 42 multiplied across, and then take sine inverse to figure out what theta is. And this value, we're looking at the nearest degree for this question. This calculates to approximately 12 degrees, which means if the angle down here, theta, is 12 degrees, the bearing of the red 175 line from north is going to be 63 plus 12, which is equal to 75. So the plane must fly on a bearing of 0.75. Okay, so the main skill to focus on here is being able to interpret a question and draw good diagrams that are going to make your working out much more coherent and just make your life way easier. Okay, beautiful. I think that's it for this question. We can move on to the last E4 level question, which is a horrific bit of geometry from 2021, I believe. I might have to double check that year because there's a lot of 2021s. But anyway, part I is asking us to show that useful result we used about 10 minutes ago, which is that a dot product of a vector with itself is equal to the vector's magnitude squared. Then that's going to be instrumental in proving part 2, which is a really challenging application of geometry and vectors that we'll get to in just a minute. For part I, very straightforward proof, definitely worth memorizing or just understanding, I suppose. Just let a vector be a generic vector. It's got an x component and a y component. We're going to take the dot product of the vector with itself. So xy dotted with xy. So we're going to multiply the x components and get x squared, multiply the y components and get y squared. Now we can pull a sneaky and we can put in a square root with a squared, because the squared and the squared cancel each other out. Now the right hand side looks like the magnitude of a vector, which is square root x squared plus y squared. It's the magnitude of the vector squared, so it's equal to magnitude v squared, QED. That's all you got to do for 1 mark. Quick, simple proof, worth knowing. Okay, we're just going to jot that up there because this result is going to come in really handy at some point in this 3 marks here. We have a trapezium. We have BC parallel to AD, and we have AC is equal in length to BD, which definitely doesn't look like it. This is very much not to scale, but anyway. Vector AB is going to be A. Am I going to put that on? Yep, vector AB is A. Vector BC is B. And then vector AD is vector BC, but it's a little bit longer. It's been multiplied by K. So this vector here is a scalar multiple of the green vector. Okay, using part I or otherwise, show that 2a dot b plus 1 minus k b magnitude squared is equal to 0. Okay, so where do we even begin? Well, the clue here in the question is right here. The length of AC is equal to the length of BD. This is the fact that we are going to use to create a vector equation to prove this part here. Warning you now, this is going to get pretty hectic. Let's dive in, let's be brave. Okay, first of all, vector AC. We can see here, vector from A to C is equal to vector A plus vector B. That's just your baseline definition of vector addition. AC is A plus B. Our vector for BD, which is from the endpoint of red to the endpoint of blue, well, if you're going from this vector to this vector, you're doing this vector minus this vector, okay? That again is just baseline knowledge from my vectors video. A vector from the end of one vector to the end of another is the end point minus the starting point. Okay, so that's just like AB equals B minus A type stuff. All right, there's the setup. That's what we're going to replace in our equation here and say AC is equal to A plus B and BD is equal to KB minus A. So putting that into here, we have the magnitudes are equal, which means that the magnitude of A plus B is equal to the magnitude of KB minus A. Now when we get to this point, we're going to get our part I involved, and we're saying, all right, so we're looking for magnitude squared so we can use the result from part A. So we'll take our equation, because there's magnitudes on both sides, and we're going to square both sides. So then we can apply the property from part I and say, well, a vector squared is equal to its own dot product with itself. So we're going to write the left-hand side as a plus b dotted with itself, dotted with a plus b, which looks pretty scary. Looks like this. The right-hand side, the magnitude of a vector squared is equal to its dot product with itself. Now we're going to try and expand this and try and make it look nice and try and make it look like the target here for 3 marks. So expanding out the left-hand side, we get, with a bit of room, expanding out the left, we get a dot a at the front. We're then going to get a dot b and b dot a. So we're grouping these together as 2 a dot b. Then on the end, we have b dot b. Over on the other side, we have kb dotted with kb. Then again in the middle, we're going to get kb with negative a and negative a with kb. So we're grouping them together as negative 2 times kb dot a. Doesn't really matter what order they're in. Then on the end, we have negative a dotted with negative a, which is positive a dot a. So we're basically just doing like a big FOIL perfect square expansion here. Same properties apply for dot products as multiplication. Okay, now we see on the left-hand side and the right-hand side, we have an a dot a, so we can just sort of wipe them away from both sides. We're also going to bring the 2 k's out of our b dot b, bring them out the front and write them as k squared. So factoring k and k out of here to look like this. We're also going to factor the k out of this one to write this as minus 2k times a dot b. So we're just going to have some common terms grouping together. As I said, the a dot a is cancelled out off both sides. Now we want to have something equal to 0, so let's bring everything over to the left as the target is starting to look like. Everything over to the left, we're going to have 2 dot a just here, and we're going to put the 2 inside actually to be really sneaky. We have the 2k a dot b bringing across to the left and becoming positive, and again we're just going to sneak that 2 into there. The reason I snuck the 2 into there on the first bracket and in the k bracket is because if you look at the target has got a 2a dot b in it, so we're going to have that in our proof somewhere. We have the b dot b from before, and then we have k squared b dot b minusing across to the left hand side, so we have minus k squared b dot b. Hope I haven't lost you yet. I've kind of lost myself here. Okay, we're going to do some clever factorization because we have a common term of 2a dot b here and a common term of b dot b here. So factoring 2a dot b out of the front 2 terms leaves us with a 1 plus k. Factoring the b dot b out of these 2 terms leaves us with a 1 minus k squared. So that's the left-hand side, nice and factorized. We can factorize even further by writing 1 minus k squared as a factor of difference of 2 squares. So we have 1 minus k and 1 plus k. The reason we did that is because now we have 2 terms that have a common factor of 1 plus k. So we can just kind of go through and divide everything by 1 plus k. It's going to make that 1 plus k vanish. It's going to make this 1 plus k vanish. And 0 divided by 1 plus k is just still 0. So wiping those out, we have divided that away and we've divided that away. And now looking at the target, we have a 2a dot b. That's great news. We have a 1 minus k, that's great news. We're looking for a b magnitude squared, and what do you know? We have a b dot b, and a vector's dot product with itself is equal to its magnitude squared, and so we have proven the target QED. Oh my god, that was tough. If I was in an exam room situation stressing for my life, I don't know if I'll be able to pull that one out, but with a bit of time and a bit of PowerPoint, anything's possible. Okay, that was fun. Hopefully you found some value out of those questions and are feeling a bit more confident about vectors. If there's any concepts in this video you would appreciate some more examples on in the future, please let me know because I will have a bit more time before HSC to do some more extension 1 and 2 revision. But otherwise, thank you for watching and I hope you're learning and subscribing, and I'm looking forward to some more extension 1 and 2 revision over the next term. Bye for now, not forever.